sir. Yes, ma'am. Lakshmi, ma'am, you can start, ma'am.
Yes, sir. Good morning to one and all present for the webinar. On behalf of the Department of Biomedical Engineering, Arupadevir Institute of Technology, Chennai, I welcome you all for the Evolution of Bio-Implant Material session. In this regard, I would kindly request Dr. M. Ravindran, Professor and Head, Department of Biomedical Engineering, to present the welcome address.
Uh, Good morning, one and all present for this today's webinar. Actually, it's yet another webinar of Biomedical Engineering, Arupade Institute of Technology, Vinayaka Missions Research Foundation, and we are very happy to welcome you all. And we are a special welcome to our guest speaker of today's session, Dr. R. Narayanan, and is a very good friend of mine. We work together previously and is actually a very good person to have nice interactions and research. And on this occasion, I would like to deliver my sincere thanks to our management and our Chancellor, Dr. A.S. Ganesan, for always supporting us in all aspects of our curricular, co-curricular, extracurricular activities. And the today's talk on bio implants is going to be a wonderful talk, which is going to kindle all of us on bio implants. And I personally know Dr. Narayanan for a few years, and he did his PhD from IIT Madras and material science. Then he did his postdoc in South Korea, and he holds journal publication, wonderful journal publications, few in Nature, which is actually having an impact factor of 30, I guess, if I'm right.
Yes.
So I understand he is the perfect person for the talk, and I hope this is going to be a wonderful session where it's going to help the young minds to get insights about bio implants and start working towards the materials on bio implants. And I wish all the participants to have a wonderful session ahead. And I would like to hand over the session to Lakshmi ma'am to just carry it forward. Thank you.
Thank you, sir. Now, I would like to enlighten few words about our today's speaker. Dr. Narayanan completed his bachelor's in metallurgical engineering from PSG College of Technology, Coimbatore, and master's in metallurgical engineering from IIT Madras. He has completed PhD in materials engineering from IIT Madras as well, and worked on thesis topic of anodic oxidation and cathodic hydroxyapatite deposition of titanium for biometrical applications. He did his postdoc studies from Koengpuk National University, South Korea, and worked on surface modification of titanium. He has published research articles in many leading journals and has also undertaken federal and industrial consultancy projects. Currently, he is guiding many PhD research scholars. We are very much delighted to have you as a speaker for today's webinar session, sir. Now, I kindly request our today's speaker, Dr. Narayanan, to please take over the session.
Thanks, ma'am. Thanks for the introduction. I thank the management of AVIT and the Department of Biotechnology and Biomedical Engineering.
Medical, yeah.
Biomedical Engineering of AVIT for giving me this opportunity to address this gathering. I hope there are quite a few, lots of students especially. I thank Dr. Devika, Dr. Ravindran, and Mr. Prabhakaran for giving me this chance to talk to you. As was introduced, I have been working on an implant from the viewpoint of surface modification, especially of titanium. And this talk would be an overview of evolution of metallic implants. And I will also touch upon some details about polymers and ceramics and composites. And later on, we will talk about the scenario in India. So probably 30 minutes on the evolution, and later on a few points pertaining to India. And we'll finish off by 10:50, and I may take some questions till 11. So before going to this implants, I'll just introduce that implant material can be any material of metallic or ceramic or composites or polymers. So depending upon the usage, It can be a metallic implant, say for bone purposes, or it can be a polymer for bone cement applications, or ceramic for bone itself, for bone replacement or for bone joining, or maybe a composite which can do a perfect job of many functions. So I'll just introduce these materials if you can understand. And we were also informed that there have been working VAT on the nano. So we will also just touch about the use of nano materials with respect to the bio-implants and their addition and cell recognition so on. So I'll touch upon the various classes of materials and then little bit of nanoscience, and then we will go on to the need of surface modification and surface modification of titanium, a very inexpensive and feasible work that is possible. And then we will go on to an Indian scenario and later on some, I don't say cutting edge, but important works that have been carried out in the last 1 or 2 decades. So with this, I will introduce. So this will be my slide arrangement. So I will go on. So you may see here that the development of materials. So all these are put into use. So probably in the olden days, they used stone, skin, wood, clay, and so these are the clay is a ceramic material. Stone is again a ceramic material containing a lot of oxides. Whereas the skin is a polymer material. Okay. Then this probably could be a stage one. Then stage two, we talk about potteries. The pottery, especially you should know about the China clay. The China clay is a ceramic, and you will know that the China clays are used for making the porcelain cups. Porcelain is a very good pottery material. Porcelain is a very good pottery material. And this word ceramic itself means hero moss. That means it has to be used only in the burnt stuff. You may see here, this ceramic material is used to make a certain shape, say a bowl, but it cannot be used as such. The green component cannot be used. It has to be burnt. Okay, so this is called as a green stuff made up of a ceramic. But this cannot be used without burning. So it has to be burnt, and then only it has to be consolidated, probably by sintering in heat. Hence, the component what you use probably a porcelain cup or other material are all burnt. Hence the name moss. So ceramic. Then we come to this. Later on, when metals were developed, people used the heat treatments or you may wonder why I'm talking about all of these in the implant. But if you know this, for example, I've been talking to you about titanium, but the titanium has certain limitations and has to be added with other elements to make it more amenable and of better usage. Okay, so that is why this slide. So you may have to modify the existing material by any heat treatment or by the addition of other elements. Okay, these could be on the metal side. Then the last century, we developed polymers, and we had all these the PET bottles. Okay, now I just give an example. When you talk about metal, we talk about stainless steels, we talk about chrome, cobalt, we talk about titanium on the metal side. And you may also know that elements like gold, silver are used for dental applications. When we talk about ceramics, we can talk about the bone cements, basically calcium phosphates. So the calcium phosphates are used for the bone reconstruction or for bones cement. So the ceramics are used like this. And then the polymers, nowadays polymers are coming in a big way. Polymers like polymethyl methacrylate, which is useful for bone cement. PEEK, polyethyl ethyl ketone, is being used. Okay, so these are some of the examples which will take you. The evolution has been like this. When metals were found out and put into use, probably we can say that the metals were the progenitors, stainless steels and then titanium. Okay, these could have been used probably say till 1970s. Then probably people have used polymers and then ceramics. Okay, so I mean, not that it has to be in this hierarchy, but the research mainly focused on metals in the initial stages, probably the 50s and 40s and 50s. Then they went on to ceramics and later on to polymers. And then in the 80s, combination of any two classes of these gave rise to something called as composites. Composites are very much used in aerospace industries and space. Even the tennis rackets are all made up of composites. Okay, so the composites also used in the biomedical applications, which take into account the better properties of one class, say metal, and other class, say ceramic. So with this, okay, now, the properties, this is general. You can talk about mechanical properties and so on. So when you talk about an implant, the implant, when, let us say it's a metal, it should stay inside the body. So it should have certain stiffness. It should have certain stiffness. It has to stay till the uh, design life. Suppose an implant, suppose a fracture had happened, you cut open, you place a material, say titanium or stainless steel, and then close. So this has to stay on for a long period. So the material, the stainless steel or titanium should have sufficient strength, sufficient stiffness. It cannot, it cannot come off. It should not crumble. It should stay. So this value is given by stiffness in terms of elastic modulus. It should have good strength. It should have toughness. I mean, toughness means it should not be brittle. It should have sufficient tough character. Suppose there is a crack, it should not yield. It should not give way. Okay. So any metallic material that is usable inside the body by way of implants should have sufficient strength, toughness, as well as stiffness. We will not worry about these. And we will talk about the chemical reactivity. So when you talk about an implant which is placed inside the body, the implant is facing uh, all the time. It faces the body fluid. The body fluid is made up of sodium chloride to a high level, 8 grams per liter of fluid. Now what happens is, so under this condition, this is highly corrosive fluid. So the metals should not only metal, the materials, whether it's polymer or whether it's metal, should not degrade. So the implants should have high resistance to the degradation by the body fluid. Okay. So any choice of any material should first of all uh, must be capable of having these properties and also chemical properties like external corrosion resistance. Okay. Okay. Now you can also build upon these properties to a certain extent by your processing. So as was discussed, you can also do some processing by careful processing of obtaining a very clean material, say stainless steel or cobalt chromium or titanium. Very clean material can be obtained by proper processing methods. So this processing will lead to very good structure. And if you can control the structure, you can get water properties. I said, I talked about corrosion resistance, I talked about strength, stiffness. And if this is ensured, we can also ensure the performance inside the body. Okay, so even a small mistake here, whether done intentionally or without intention, will ultimately affect the performance. Okay, so this is just like having a car. You buy a car either of worth of 5 lakhs or 50 lakhs and is performing say for about 10 years, and later on it may have a crack. Okay, this crack could have come from a structure, poor structure, which could be the which could have come from a very bad processing. Okay. Similarly, the implants also will perform better if all these are excellent. It is done through very good processing, uh, very good processing, and then has very good structure. So why I emphasize all this is because very good, because it has to go inside the body. So the body should not elicit any wrong reaction. Okay. Otherwise, the patient will feel a lot of excruciating pain. Okay. To avoid this, you should have produced a defect-free 99.99 purity. They call it as a 999 purity, 99.99% purity. This is in general not possible. Okay. In case where it's not possible, in case where such a processing is not possible, you can also modify the surface of that implant accordingly to produce a desired chemical performance or a desired metallurgical performance, a desired biological performance possible. Okay, so that is also possible. So therein comes the surface modification. So to a certain extent, we have to produce a clean material here itself, and all these should be the objectives. In case this is not possible to a great extent, we can also modify the surface of this implant through proper means to obtain the desired properties, to have better chemical performance or better performance inside the body. This is also possible. This is one sample of a material. You may see that, okay, you can see this can be thought of as a grain. So the magnification is very high. You can imagine this to be a grain. Probably, yeah, you can see that this is sort of a grain. Okay, when we talk about nanocrystal materials, so this size, this dimension is of the order of few nanometers and seldom exceeding 100 nanometers. Okay, so this has to be seen only at a very high magnification. So this is a small entity inside a component, either a metal, a polymer, or a ceramic will have grains, and if the grain dimension is of the order of nanometers and size not more than 100 nanometers, the material is called as a nano material, nano sized material. And what is the need of nano sized material? You know, the body consists of cells. The body consists of bones. The bones are made up of osteoblast. The skin is made up of fibroblast. Coming to the bone, it is made up of osteoblast. The osteoblasts themselves are of few nanometers, and when the implant is also of nano-sized dimension, or the coating, the surface modification, the coating is also of nano-sized dimension, the cells can easily recognize them. So that is the reason why the cells which are of nano-dimensional character can easily recognize the implant material or the coatings in case of if they are also of nano sized, then they easily recognize. The recognition will be easy. So what is the repercussion of this? The cells will easily attach to this implant surface. Okay, so therefore you have better bone bonding, bone implant bonding. What is the result of this? The bone will set faster. So therefore the reconstruction will be very easy. It will not take much time. So yeah, very simple, the nano-sized, nano-dimensional material, nano-dimensional crystals of material will finally help in your better bone bonding and ease of bone setting. Okay. So we will probably ignore this. Okay. Now, I told you about different alloys. When we talk about metallic materials, we have we have the ferrous alloys. We have ferrous materials in which we use only stainless steels. Stainless steels are used. There are different types of stainless steels, and the implants are made up of stainless steels of austenitic grade. But the problem there is they have very high density. I mean, a high density means per unit volume, they weigh more. Okay. But what happens is the patient should carry heavy weight for a small volume. So he will have he's already having a body weight, say of 60 something kgs. And if a small portion, say elbow or hip or knee, is placed with a heavy metal like stainless steel, then he will feel excruciating pain. So that is one major disadvantage of stainless steel. Secondly, stainless steel is composed of nickel, and as I told you, uh, it is always placed inside the highly corrosive body fluid. So in such a case, what will happen? The nickel of a stainless steel comes out, it dissolves out. And if nickel comes out of the stainless steel system, stainless steel loses its integrity. And the leached out nickel travels throughout the body stream and can be carcinogenic. Okay, this is the problem with stainless steel. I told you about other alloys. People use titanium. Titanium is very good. Titanium is extremely corrosion resistant and it has a low density. So compared to stainless steel, it has only 50% of this, 40 to 50% of this. So this is a much lower weight material. It has high strength. It has very good corrosion resistance. But the problem with titanium is when titanium is placed inside the body, it has poor frictional characteristics. That means it tends to rub more. Compared to stainless steels, titanium tends to rub more and can cause friction. Okay, when it is placed inside the body, when there is a metal to metal contact, then titanium will give very good, very poor frictional performance. Okay, so this is one major problem with with titanium. We can also go for cobalt chromium. Cobalt chromium is also being used, but there also the problem of friction is very high. Okay, so as far as the metallic system is concerned, stainless steels, titanium, and cobalt chromium are used in large quantities. Okay, tight and magnesium is the lightest of all metals. Okay, so therefore magnesium, when compared to titanium, magnesium weighs only half per unit volume, or even 70% of titanium. But the problem is magnesium is its corrosion resistance is poor. That means when you place inside the body, magnesium will lose itself. So, compared to titanium, which can stay for even a very long period of 10 years to 20 years, magnesium will not stay. So, magnesium has poor corrosion resistance and it tends to resorb. It tends to dissolve inside the corrosive fluid. So, that is why, although a lot of research has been going on in magnesium, it still cannot enter the titanium market. Titanium is supreme only because of this high strength to weight ratio and high corrosion resistance. But the negative factors here are frictional performance and its availability. With respect to India, titanium system is generally not available. So therefore, surgeons even though prefer stainless steels. Okay, we will ignore aluminum. Okay, magnesium, I told you, titanium. Titanium, a lot of now we compare. Titanium can be a pure titanium, which is used in dental applications or the alloys. So here you can see there are different alloys. I told you there can be two phases, alpha phase and beta phase. It has low density and it is generally available as alpha phase. When you heat to higher temperature beyond 900, you get a beta phase. Now, when you have alpha and beta, it's even stronger. And what happens is, if you remember my first slide on the specific stiffness, the elastic modulus, when you place inside the body, the metal should have matching elastic strength. Bone has a elastic modulus of 20 to 30 GPa. So any material placed inside any metallic material placed inside the body should have matching value of 20 to 30 GPa. Stainless steel is not having that. So also is cobalt chromium. Titanium is very good from other points of view, as I mentioned earlier. But unfortunately, this alloy, the alpha plus beta alloy, the titanium 604 vanadium has a high elastic modulus. So compared to the bone, which has a modulus of 30 GPa, this Ti 6R4V implants have very high modulus of 130 MPa, almost 4 times higher. Now, what happens is when you place these implants for their other beneficial properties, there's a stress shielding effect. It means this titanium will tend to stay, but the bone will sacrifice. The bone will be the sacrificial lamb. Okay, so therefore, research has been going on to make titanium alloys using different elements, for example, niobium, zirconium, or titanium, but with a view of reducing the elastic modulus. Say from 130 to 107, people are nowadays even making 60 GPa. Of course, these are not available in India. There is one such alloy, titanium, niobium, tantalum, zirconium, TNT is which is produced in Japan. Almost they have made this some 10 years ago, which has elastic modulus of 60 GPa. I mean, till now, to the best of my knowledge, we don't have any metallic material, of these classes, stainless steel or titanium or cobalt premium, which is almost close to 30, but we are very much nearing. So the TNT is that has about 60 to 70 GPa. Okay, so this probably a very good area for research. So I talked about metallic systems. We'll ignore this. Nickel is not good from the implant point of view. Then ceramics. So the ceramics are inorganic materials. They basically contain oxides, carbides, or nitrides. So this is one such application. So ceramics. In the body, we have calcium phosphates. The bone is made up of calcium phosphates, hydroxyapatite, which itself is of nano sized. Okay, so ceramics. I told you about calcium phosphates. Calcium phosphates can be used to make the bone itself or to the bone cement. So that is one way. And when you talk about the dental implants, people are talking about the zirconia, ZrO2 implant. So ZrO2 is also a ceramic. But the problem with ceramic is it has a very poor ductility. So here we form a shape like this, and it may form, and it has to be heated. Otherwise, it will not do its function. Okay, so that's why the name I said keramos. Ceramics is an English word, but the root word is keramos. It has to be burnt. It should be a burnt stuff, but it has a very poor ductility. Though it has a very high temperature performance and resistance to corrosion, but it has very poor um, forming characteristics, very poor formability. So therefore, what's the point in having all these materials without any formability? Okay, so it has there's a term used, brittleness. It has brittle characteristics. So ceramics can be straightaway rooted only from brittleness point of view. Though it has other advantages like a um, high temperature resistance, very good performance to corrosion, and so on. Okay, so this is the brittleness is one single factor that can rule out the choice of ceramics. Then polymers. I told you about polymers. I told you about PEEK, the PEEK, polyethyl ethyl ketone. PEEK. People are even using chitosan. This is again a polymer. So these are very good. These are very good formability. They're quite opposite in performance to ceramics. As I told you, ceramics are very poor formability. That means ductility, whereas the polymers have very good bending nature, very good formability. But they cannot be used beyond a certain temperature. Say beyond say 300 degrees. Of course, you have thermoplastics, but still 300 or 400 degrees, they cannot be used. They don't have high temperature resistance. They have, okay. Now, so because of this, I told you metals like stainless steel have high density. Ceramic, but they are very good from certain point of view. Ceramics high temperature resistance, but poor ductility, whereas polymers cannot be used for high temp resistance, and they have generally they do degrade. So because of all these, people all thought about composites. Okay, so what is a composite material? Any combination of two or more different materials at macroscopy level, and you can use a proper compliant matrix space, and you can add different reinforcement either in the form of particulates or the form of fibers. Okay, so people use a carbon nanotube as a filler. You may use carbon as a fiber. You may use a silicon carbide particle and so on, or in the ceramic reinforcements on a metal matrix or a ceramic matrix. So why do you need this? So when you make composite, whatever be the nature of the individual group, the the disadvantages of the individual group are overcome by having a composite material. You can choose appropriate reinforcement base on an appropriate continuous matrix, appropriate quantities, so as to get all these properties. This is very, very useful from biomedical point of view. So this is only generic. We can have a polymer matrix, continuous matrix of polymer, say polymethyl methyl, the polymer methacrylate, the bone cement, whose strength is generally low, and you can augment this strength by the use of say zirconium oxide or titanium oxide ceramic. Okay, so then you get a composite of titanium oxide particle or zirconium oxide particle in a compliant polymer matrix. So this sort of composite is used in dental applications. Okay, so composites can be tailor made. So you should have a reinforcement phase, yeah, fiber like this, carbon fiber or CNT, and a resin, so as to make the matrix. And then we can play with the orientation. We can play with the size to get different texture, but you can get different properties. So this is all possible. And as you can have a metallic matrix or a polymer matrix or a ceramic matrix. Okay. So with this, now, now I think we can. So now, what's a biomaterial? Your biomaterial may not be an implant alone. A biomaterial can, is a material placed inside the body, consisting of a metallic system or polymer or ceramic system or combination of these as a composite that is placed inside the body, and when it comes in contact with the tissue or blood or biological fluids, should not adversely elicit any reaction. Okay, any biomaterial can be of these classes, any one or different types of these classes that placed inside, when placed inside the body, or when it comes into contact with the soft or hard tissues or blood or biological fluids or prosthetic or dental, whatever be the usage, should not create any adverse reaction. So this is the main thing. So this sort, a lot of definitions for biomaterial. This is given by Professor David Williams. So these are some of the materials. You can see the hip joint. You can see the hip joint. This is a metal. This is a this can be titanium metal, and this is a cup. So this is one unit. This is another unit. This has to be fixed using the bone cement, the polymer methacrylate, the heart valves, the breast implant. These are the polymers. So here we have the titanium metal, which is fixed with this using a bone cement, polymer bone cement. So we have a heart valve, a polymer, the breast implants, a silicone gel, a polymer, in artificial hearts. We also have IOM. This is again a polymer. So all these are put into use. Now the eyeballs are made up of zirconia these days. So now you'd understand the elaborate the introduction about this system. Instead of directly going to the biomaterial or implants, I dealt a lot so that now we can understand the further slides easily. So just some historical background. People used gold, even though people use gold for dentistry, for braces. And I told you high strength materials like stainless steels are used, and then glass. I told you about the hard ceramic, the keropos, the porcelain, or zirconia used to replace iron. Zirconia is a ceramic, is used to replace iron. That's purely prosthetic. And the olden days, people used wood instead of metal for making limb processes. Okay, what is a bone? Bone is a composite consisting of mm, nanocrystalline calcium phosphate in a collagen matrix. Okay, bone itself is a composite containing nanocrystalline calcium phosphate ceramics made fused together and bonded together using a polymer called collagen. Okay, so probably this earlier they used to have this structural biomaterials, then used for soft tissue replacements and functional tissues, and then you go for engineering constructs. Probably here you can think about the implants like a titanium alloys or stainless steels coated with the hydroxyapatite so as to have a better bone bonding. So when you talk about uh, the need or requirements for material to be placed inside the body, I told you there are many requirements. It has to have a certain chemical properties like excellent corrosion resistance, it should not degrade, and mechanical. It has to first of all strength, should have adequate strength given by the yield strength or a specific stiffness. Okay, and then when you talk about the pharmacological things, it should not be toxic. It should not have embrittlement. Okay, and then when you talk about the bio points of view, it should be compatible with cells. It should Okay, so you should have good fatigue resistance and no excellent corrosion resistance. You should have wear resistance and it should not be toxic inside the body. So these are some of the terms used. Cytotoxicity is a term used for the cell culture, and this is oral toxicity for a dental implant. Okay, so there are not one requirements. There are so many requirements, and what are materials I mentioned earlier do meet almost 70 to 80% of these requirements in general, and any such shortage of requirements can be met with by the use of surface treatment, surface requirements. So these are some of the overall requirements. Generally speaking, an overall, a single term, it should be biocompatible. Any implant is a foreign material and it should be acceptable to the tissue surface. It should have adequate strength, engineering design, as I said, lightweight, high strength, and chemically inert, and pharmacological acceptability like non-carcinogenic, non-allergic, non-toxic. Okay, and these are all from a technical point of view. And it should be available in the particular area. For example, I said titanium. Titanium is not available in India, not, so it is very costly. And even if it's available, it's difficult to fabricate. And it should have process for large scale production. A large scale production and ease of fabrication and availability can make the material available. Okay, so these are more of a technical points, and this is more of logistics. So I touched upon this. These are some of the examples. Polymers, we have nylon, silicone rubber, polyester, PT, PTA, PTFA, PTFE, then PMMA, methacrylates, then you have PEEK. So the advantage is they are easy to fabricate, but unfortunately they are not strong, they may degrade. So these are some of the examples, sutures, blood vessels, and so on. Metals, austenitic stainless steel, some cobalt, chromium, titanium alloys, they are strong, tough, and ductile. But the problem, especially here, stainless steel is density, and then whereas titanium alloys are difficult to make, are not available in India, and then they are very difficult to uh, they have very difficult the wear characteristics. But generally they are used in the bone joint replacement, the hip joints, knee joints, dental applications, suture wires, stents, and so on. And ceramics. Ceramics are highly biocompatible, but one major problem is that they are ductile. They are not ductile, they are very brittle, and they are very weak in tension. But anyhow, they are used in dental applications, zirconia as a single implant, or titanium oxide, double implant, so on. So I use a combination of these carbon-carbon and the fiber reinforced peak with the carbon fiber. So these are used uh, to make a dental resin, a bone cement. So, but the one advantage is you can tailor, you can make them, you can design them to your specification. But making is bit bit expensive and not that easy. So these are some of the materials. Silicon rubber, and these are the polymer silicon rubber using tubes. PMMA is used as a bone cement and intraocular lens. Hydroxyapatite is used as orthopedic and dental devices, mainly as a coatings. So these have been touched. Alumina is used to make the eyeball. Zirconia is used to make eyeballs. Hydroxyapatite is used to make especially coatings. So these are some of the. You can see this. So this is a metal implant. It can be made up of titanium. You can see this is a you can see the color here. So this can be the titanium metal, titanium, pure titanium, and this the coloration can be because of some surface modification. So this is a dental implant, screw implants placed on the dental side or on the bone fasteners. These are dental implants. So the hip joint on the total. Okay. So these are some of the applications. So this is a titanium, we know this. Then I told you about situations where all the requirements will not be met. So the requirements probably have only 60 to 70% requirements met by this native implants. And in such a case, to increase its level of application, to increase its throughput, to increase its functionality, surface modification is done. This is done on any metallic implants and more notably for titanium implants. So what do you do? I can improve the surface roughness for better bone bonding of the implants, or I can alter the chemical. As I told you, um, the cells contain hydroxyapatite. The bone is made from hydroxyapatite. So my implant can have hydroxyapatite as a coating. So the titanium implant containing hydroxyapatite can easily attach to the bone. This is one strategy. So another strategy is to coat the biological molecules themselves, maybe the peptides or collagen and so on. Okay, so with these objectives of uh, having a matching surface roughness or matching chemical state or matching biological state of titanium implants, there are many techniques used. These are the techniques. So anionic oxidation is one such way of promoting a corrosion resistant layer to improve surface roughness. This is one way. Or hydroxyapatite can be coated on titanium implants to improve its surface chemistry and also enhance better and also enhance the bone bonding. You can also go for peptides, the protein coatings or collagen or fibronectin, so as to improve its biological state. So my PhD was on this anionic oxidation and this hydroxyapatite deposition. This is a very inexpensive technique. Whereas IR implantation is also possible, but it needs a lot of time and lot of energy, and it's a expensive technique. So these are some of the techniques even commercially practiced for improving the surface of titanium implant, so as to improve its bone bonding characteristics. So I think this is more of the oxides. So you can these are some of the tools used. Once a coating is made of an oxide on titanium, so I'm just referring to this technique. Once an anodic oxide is made on titanium implant, we have to measure certain properties, evaluate surface morphology, or whether it has, you can see the titanium contains oxide film. This is ensured through X-ray diffraction. You should can also analyze the surface roughness. You can see here it is high and here it is low. So the oxide is of such features. This oxide is coated on titanium. So the analytic oxide contains a certain Ra roughness, and it has certain wettability given by this contact angle. So these are the details about the analytic oxide. And what you do is you do the cell culture. Whether the cells do adhere or not is given by this in vitro test. You can see here that the anodic oxide film. The anodic oxide film shows the anodic oxide film shows better um, in vitro properties and testing in animals using rabbit models. It has been shown that the performance of the oxide coated titanium is better after 6 weeks and 12 weeks. So what do you measure here? You place the sample inside the body for say certain predetermined time, for say 6 weeks or 12 weeks. After this time period is over, you sacrifice the animals and cut a small portion, and you can see this metal is very rigid or not. So you can use that the removal torque values. You can see that the removal torque values are high for the anodic oxides. So this way you can ensure that this oxide coated pieces are stable and rigid and attach very firmly with the bone. So this is one way of test. So this can be easily replicated in human beings in the clinical trials. So this is the in vitro cell culture studies or in vitro bioactivity studies, and this is in vivo animal studies. This is one example. So that covers the use of titanium implants to start with, which have very poor frictional properties and whose chemical nature is altered by roughness altered by oxide coating, and which has a very good physical characteristics shown in the morphology, and very good biological properties shown here by the in vitro studies and also in the in vivo animal rabbit studies. So this is the general morphology. So this is you can see the cells spread. So this is a surface, so maybe oxide surface on titanium. So I treat it with osteoblast the cell for certain days. Say after 3 days, you can see that the cells spread. This is the starting cell, and it has extended its arms. Okay, so this shows that my oxide coating on implant are very useful. So when it is placed inside the body, the cells will attach firmly and then spread. So this spread, this cell is attached to another cell here. This cell is attached to another cell here. That means there's a cell connectivity, and therefore there will be better bone bonding compared to the surface without this oxide coating. So that's what it means. So these are some of the. So I had talked about anodic oxide. Then we will talk about different bioceramics. You know, so you can see that the bone is made up of this is the bone. It's made up of hydroxyapatite crystals in collagen matrix. So when you can coat your titanium implant or stainless steel implant with hydroxyapatite, then the cells will attach easily. Since the bone, natural bone consists of this, if I can have a titanium metal with this, when this is placed inside the body in the vicinity of the bone, then the bone cells, the osteoblast cells will easily attach to the implant. So with this idea, we try to produce a titanium implant surface with electrochemically formed hydroxyapatite. So this is the There are many techniques available, but we are interested only in this. So this is again, that means on a titanium implant surface, a hydroxyapatite coating was made by a very simple, inexpensive lab level cathode deposition. The details are available here, and you can see that this is the surface morphology, and the presence of hydroxyapatite is indicated in X-ray diffraction and TEM. And this is the biological studies. You can see that the pristine surface has certain levels of cytotoxicity, whereas the hydroxyapatite coating shows improved cell digestion and no toxicity. And the coatings also develop proteins in the vicinity, which indicate their surface active state. And when cells are placed near this implant, the coated implants, the cells do elongate. This is called a filopodia extension. So the result is my nano-sized hydroxyapatite coating can be used on implants and placed inside the body. Then, another study is that bone is not only made up of calcium and phosphate; it also contains other ions like magnesium, sodium, strontium, and bicarbonates, so on. Nowadays, you can see that a lot of people have this very poor bone density. When you go to the doctor and there's a bone defects, the bone become porous. When you go to the orthopedic surgeon or the doctor, he would suggest the use of strontium granulate. In other words, the strontium ions, strontium granulate tablets suggested will help in filling up the bone defects, the bone pores. So the strontium ions help in better bone density. It improves the bone density. And there are many such metals. For example, the bone consists of all of these strontium, magnesium, silicon, silver, and each one has certain properties. Strontium is very good in healing osteoporosity, whereas silver is antibacterial. Even low quantities of sodium are present in natural bone and in tooth mineral. So therefore, there has been significant interest on the study of effects of these various substitutions of HA. The hydroxyapatite, the calcium phosphate can be added with these ions of magnesium or strontium or silver or this bicarbonates, and that study can, that coating can help in much better augmentation of the bone implant bonding. So in this study, in this view, certain studies have been done in which silver, silver has been used. Go down. In which silver has been added. So hydroxyapatite, which is a calcium phosphate, is augmented with the addition of silver, and you can see that the silver is present in XRD, and silver shows very poor dissolution. Okay, or in other words, the silver substituted hydroxyapatite shows very poor dissolution compared to the absence of silver. That means the silver helps in stability. Silver is also antibacterial. This is one such study. So why I'm talking about all this is because so we started from metals, titanium, and we went on to production of alpha plus beta. Titanium 6, we can modify the metal itself, and in case the properties are not good enough for fitment in inside the body, you can also modify the surface, and the modified surface can be with respect to improvement of surface roughness or surface chemistry, chemical stature, or biological state. So in this regard, we dealt on anti-oxidation and cathodic hydroxyapatite, and with the view of improving the hydroxyapatite and to supplement with different ions like strontium or silver, coatings have been produced. Okay, so this is basically an evolution of so the body implants. Coming to the research areas which could be interest of which could be of interest to the young researchers. Titanium alloys, as I told you, are being made. So pure titanium is added with aluminum or vanadium or aluminum or niobium, zirconium, tantalum, copper, manganese, mainly to prevent the stress shield effects. So the idea here is to reduce the E value from 130 or 100 or to matching values to bring down to 40 or 50. People have succeeded in producing alloy of titanium, niobium, tantalum, zirconium. It's called the TNT, is it? Which has a E of 60 GPa. This is one area of research. So the other area of research is use of zirconium oxide, ZR-2, the single dental implant, screw implant, as against the two pieces of titanium. This is one such area. And magnesium has been used as a resorbable implant material. Unfortunately, magnesium dissolves even before the desired lifetime. So if people can come with certain additions, magnesium with calcium or magnesium with zinc, which can improve its resorbing nature, it will do a very good service because magnesium has very lightweight. So compared to stainless steel or titanium, magnesium is much better in this. And then I told you about use of strontium for preventing osteoporosity. Titanium foam is also used. Foams are being used. And then from the surface modification point of view, we can have a carbon. You know, carbon fiber is used. Carbon nanotubes are being used. We can also have a very hard carbon. So diamond-like carbon. Even this diamond can also be made into nanoform. So diamond-like carbon coatings or nano-sized diamond can be coated on titanium for increased strength. And this diamond is non-corrosive and highly compatible. And people are using other powders, zirconia powder, etc. And we can use different production techniques. And coming to 3D printing, the additive manufacturing, generally people use ceramics, means people use polymers so as to customize a certain component and prepare it on 3D printing using laser or using electron beam. And this can be customized and can be studied externally before being put into use inside the body. But in abroad, people, especially in the advanced countries, people are using metals like titanium or stainless steel to 3D print. But in India, we still use polymers. Metallic 3D printing is a very, very costly affair, which is a multi-billion-dollar industry. And India cannot afford it. So people generally use only polymers. Nowadays, there are many students even using the polymer 3D printing. And my area is a texture property correlation. As I told you earlier, you can have different in the composites, you can have a different orientation. The properties are being studied. Okay. These are on the metals or molds. But on the composites, on the polymers. So I told you about PMMA, polymethyl methacrylate, which is a bone cement, and the peak polyethyl ether ketone. It's also used these days. The peak nanocomposites formed with peak with carbon fiber, peak with hydroxyapatite are also being tried. Of course, it's not a commercial. There's one company in Europe which is trying to make it commercial, but it can take time. So these could be some of the research areas in this, especially in the bioimplants. Uh, and okay, if you're interested in devices, you can go into devices and using mechatronics concepts like you can make sensors, actuators, pliers, etc. So that's a different ballgame. But this is from the purely materials point of view. You can promote different metallic systems or ceramic systems and play with the different morphology and can go for different types of coating, surface modification coatings, different manufacturing technology and so on. These are some of the areas. And why do you need this? It's mainly because of this. In spite of the current size of Indian market is about 2,400 crores, and this is a statistic we saw a few years ago, and there's a projection that in another 20 years, this definitely will improve from 2,400
யாரும்
crores
நிக்கிற மாதிரி இருந்துச்சு இது.
to 16,000 crores. It will definitely increase. And you can probably see a growth rate of 7 to 7.5% every year. So therefore, there's definitely a need for research in India on the implants. And not only this, there's COVID. The government has taken a lot of initiatives. Private players have taken a lot of initiatives on producing the COVID combating mask or sensors and so on. And besides this, we have traditional diabetes, obesity, and the elderly people showing osteoarthritis, osteoporosis. So, to address all these issues, or some of these issues, so research in India on the implants are gaining attention. So probably the Indian youngsters, the young researchers, have to pay a lot of attention towards these, and there will be definitely scope for improvement on this. There can be federal funding, there can be private funding, there can be interdisciplinary research consisting of scientists, engineers, vets, and medicos. Okay, so and there's a scope for everything in the knee, some statistics of the TTK, Sharma Orthopedics, or some of the important players, the private players in the knee implants. So you may, I just end with this last slide. This slide talks about people are working not only on the larger metals. You may sometime back, say some 5 years ago, there was one gentleman from MIT, USA, who worked on deformation of malarial cells. You generally will think of food-sized metal samples being put in tension. But this professor has studied the deformation characteristic of a nano-sized cell in tension, and he found out that this cell shows very poor deformation, and that is why when you are infected with malarial cell with poor deformability, you have a lot of pain. Okay, so this was published in 2005. Professor Subrasuri of MIT. So people use such an advanced research, not only from an evolution of previous decades, previous centuries. We go down to advanced research, which is published in 2005. So this information, wherein a single nano-sized cell being pulled in tension to show its poor deformability, was published as recently as in 2005. So you have to use all the modern tools like lasers and the nano machines, nano robots, and so on. Okay, so this can be extended to other cells also. Instead of malaria, you can go for typhoid cells, and then you can. This data will be useful in developing better drugs. So with this, I close this session, and thank you all for attending this session. Thank you. I hope I have not taken much time.
Thank you, Professor. It was actually a nice session. It was really thought-provoking, and you've given so much of inputs. Prabha,
Yes, sir.
can you just check if anyone has any questions? We can go ahead with the question and answers.
Yeah, I will take a few questions.
Yeah, sure.
Yes.
And I too have few.
Yeah.
Participants, if you have some queries, you can ask now. The option has been enabled so that you can unmute yourself and you can ask. If you have any queries from the participant side, because the lecture was very much useful for all of us, and it is a thought-provoking process on bio-implant. So obviously you should have many questions inside you. So you can come up with the questions either in the chat box, or you can personally unmute yourself and you can ask. So one question has been raised, like, sir, can we regenerate synovial fluid?
Yes, you can. Synovial fluid. It's what we call as a simulated body fluid. So whatever I showed here earlier, I showed here the bioactivity. This Actually, what you do here is we place a metal, whether it is surface modified or not, inside a body fluid. It's called as a simulated body fluid. This consists of sodium chloride. There is a chemical. The formations are available. Okay, what you do is you place the sample inside the body and maintain the temperature at 37 degrees for a certain period of time. So what happens is the solution consists of calcium phosphates, calcium chloride, magnesium chloride, sodium hydrogen phosphate, sodium bicarbonate, and the sodium chloride. So there are calcium ions and phosphate ions available. So what happens is when you put inside, when you place this implant inside the body at the body condition of 37 degrees, these ions go and deposit. So these rounds that you see here, the spherulites are all calcium phosphates, which are which can be diagnosed from XRD or your SEM. So the rate at which it forms indicates the bioactivity. This is what is happening inside the body. So when you place your metal implant inside the body, the body fluid consists of calcium and phosphate ions. So they tend to attach, probably within 3 days or 4 days. So that is this is the in vitro studies which actually replicate what is happening inside the body. So the simulated the body fluid can be simulated. You can refer to Professor Kukubo, Japan. I hope all these answers.
Yes, sir. Yes, sir.
Yes, Dr.
Thank you so much for your answers. So I
Professor,
have a yeah, yes,
yeah.
sir, please.
Before that, I will ask.
Yeah, please. Sir.
Yeah, Professor, actually, you spoke about this titanium alloys,
Yes.
and I just want to know, and probably would everyone would be happy to know what is the actual limitations as far as the titanium alloys are concerned in bioimplant, like which
When you
has to be
talk
over.
about implants, generally, I would broadly divide it into two series of applications. One is dental, so other one is orthopedic. The dental applications do not need much strength. Okay, so there you may use a pure metal. So commercially pure titanium is used in dental applications, the form of screws, mainly fasteners. Whereas the body applications like the hip, the bone applications, the hip or knee, do require high strength requirements. So they need, this is a hip implant. So this needs higher strength. Hence you go for alloy. Okay, so tie 6L4B. Or to summarize, the dental applications need only pure titanium, which has lower strength, whereas the bone applications need high strength alloys. One alloy is very common as tie aluminum vanadium. Now coming to the limitations, per se, they have comparatively poor fabricability compared to stainless steels. Number one. Number two, they have very poor friction. When you place this, there's a the other slide here. This is the slide. This is the titanium implant. This is placed inside the cup. What happens here is when there's a chance of friction, they have very poor friction properties. So titanium alloys have very poor friction properties. So therefore, when they slide, they tend to seize. I think you know about seizure, which happens in an automobile because of the wear. So this is the one main limitation of titanium system. And number three, as far as India is concerned, they are not available in India. So we have to procure from abroad. Government has plans to, this actually is extracted from ore, titanium oxide, which is available in the seashore, in the sea sand. So any sea containing area, especially the southern part, Tamil Nadu and Kerala, has sea sand rich in titanium oxide. So the government has plans to make start a titanium extraction plant somewhere in the Malabar coast of or the southern coast of Kerala. It has long by the way. I don't think it has come. So as far as India is concerned, titanium plants are distant dreams. And as a poor person, stainless steels do a good job. So as far as India is concerned, stainless steels do a better job. Although titanium is technically better, there are three limitations are their fabricability, their poor friction, and their lack of availability.
So that's where we go for the alloys.
No. I mean, titanium as well. Titanium are alloys. The titanium is the pure titanium is used in dental applications, whereas the alloys, the
Oh yes.
aluminum, vanadium, or niobium, titanium, zircon, the alloys are used in the bone applications, the knee applications or joint applications. But as a whole, whether it is a pure titanium or titanium alloys, they have all these three the inadequacies.
Sorry, Prabha, please go ahead.
Yes, sir. Sir, I have one question, sir.
Mm.
Why nickel is not suitable for bioimplant?
Ah,
The reason.
nickel, what happens is nickel by its nature,
Yes.
nickel, aluminum, when even vanadium, when these, I know, let us say we place this metal.
Yeah.
Let us not worry about the nature of the metal. When you place a metal, and I told you it is surrounded by the body fluid, which is highly corrosive. We also had we simulated a body fluid. What happens is this metal, this piece is basically a metallic piece, and if this contains nickel, and if suppose this nickel comes out of this implant here, it has to enter the body stream. It is found that nickel is highly carcinogenic. So where does nickel come from? So nickel will enter the body stream only from here. Okay, and if this implant contains nickel, then this can be ruled out. So stainless steels contain nickel, almost 10 to 12% nickel, and this nickel, when it comes out, it can go through the body completely, can completely leach out and enter the body stream. Nickel is carcinogenic. There's also a problem with aluminum. Aluminum is carcinogenic, vanadium is toxic. So there are, though we use aluminum and vanadium to strengthen titanium, they should not be used beyond these limits. And people go for even vanadium replacement with niobium. So this is one classic alloy. 6 aluminum 4 vanadium is a very classic alloy, but people are replacing this vanadium with the niobium. 6 aluminum and 4 niobium. Why? Because vanadium is toxic. Aluminum is carcinogenic. Aluminum leads to Alzheimer's disease. So although you should how to use metallic implants for certain good uh, values, there are also the adverse effects like leaching out and being carcinogenic, causing diseases like Alzheimer's disease or toxicity. You should play. That is the reason why we can go for coating. Suppose you go a surface modification of coating, you may to a certain extent prevent the leaching of these carcinogenic elements. So, they are good. Probably I may give 80-90% marks, but 10-20% I have to go down.
Yes, sir. So thank you, sir. And also I have one more question. Like bioimplants, for how many days or years it lasts in a human body once it gets implanted? It is a permanent
If
structure or it needs to be replaced in a periodically?
yes, yes and no. Again, coming back to this, we'll let us stick down only to these maternity plants. I told you there are major family, stainless steel family, cobalt chromium family, titanium family, and magnesium family. So titanium is good. We can first of all, it acts as a support for the cells to form. Let us say I have a bone here, another bone here, which is broken. If I place the titanium metal, it acts as a scaffold upon which the cells can be formed. So titanium acts as a base material, just as a foundation for bone to form. Okay. Then once the natural bone is formed, say up to the level of acceptance by the orthopedic surgeons, it can be removed. It is not necessary that it has to be removed. So titanium can stay for a longer time, for 10 years, 20 years. Why? First of all, it doesn't corrode. It is mechanically stable. It stays here. Any any movement, any microatomic movement doesn't impede. Okay, it doesn't dispersion itself. It doesn't corrode. It doesn't leach out. Okay, so it stays perfectly, even for longer time, say 10 years or 20 years. But the case of magnesium, the bone may take certain time. We studied, say, up to 3 days or 5 days, maybe 2 weeks. The bone cells tend to form. But what the titanium will stay till that time as a scaffold. But what happens in the case of magnesium is magnesium itself will corrode. Okay, though it is lightweight, but magnesium will corrode, and it doesn't even stay that full period for which the cells need to form. Okay, if you ask me a question, it depends upon the appropriate choice. Whereas in the case of stainless steel is good. It has a lot of life, but you should see that the nickel doesn't come out. Okay, so it's a it's a customized. So my general answer would be from the longevity point of view, it would be better. I know of cases wherein it has stayed for even 20 years. So, well, it again depends upon the area. It can be for an elbow, it can be for a hip. So it depends upon the load also. But generally, from technical point of view, titanium stays for a longer time, whereas magnesium doesn't.
Fine, sir. Fine, sir. So thank you so much, sir. And I also have another question.
Mm.
Test method for uniform coating of the substrate.
Best
So,
method.
yes.
Yeah. See, let us say that you want to improve the roughness or the chemical state or biological state. I had a slide, but I didn't show because of want of time. There are different techniques of coating. There are different techniques. Let us say that you want to improve the chemical state and you want to deposit hydroxyapatite. Okay, on to metals. It can be a stainless steel metal, or it can be cobalt, or it can be titanium. On these implants of your choice, you are trying to promote a coating of hydroxyapatite. Okay, now with this, there are many methods. I use this technique for my studies, but plasma spraying is also used. There are advantages as well as disadvantages. Plasma spraying is generally used in commercial method, not only for this, it is useful for engineering coatings also. Even a wristwatch contains a golden glow color. This is because of titanium nitride coating. This is produced from plasma spraying. So this is being used. Plasma spraying is commercially useful for depositing this. But there are certain problems. Probably there will be uniformity, but it is generally porous. Whether it is good or bad is again a debatable issue, and it can form a lot of volume. I mean, thickness will be high, but the outer layers tend to come out. Okay, so there's this called the delamination. So layer by layer removal is possible. So it's called the delamination. Plasma spraying is generally acceptable uniform coating commercially, not only for medical grade, even for engineering grade coatings. But there are a few problems, but I think overall plasma spraying will be better. There are different types in this. I told you about the DLC coating. If you are so the DLC is produced by plasma spray. You can coat any ceramic, any metal on any metal. You can coat anything on anything. So that's a universal technique, plasma spray. But these are all, and sputter techniques are expensive. Electrophoretic and electrochemical has certain advantages, but there are also some disadvantages. They may not be used commercially, but for commercial grade, I think plasma spray is good. In fact, if you look into this, I've shown a slide wherein the TTK uses company TTK, and TTK does this plasma coating on the existing implants, and they charge heavily also. So the TTK pharma, the TTK company uses plasma spray to coat, I think DLC on implants, metallic implants. So plasma spraying would be a better bet, safe bet. I hope this answers your question.
Yes, sir. Thank you so much for your answer, sir. So is there any other questions from the participant side you can ask? So if there is no any questions or if the session is very clear, then we'll go for a conclusion. Santoshini ma'am, can you please take over?
Yes, sir. As an end comment, I would like to sincerely thank our management for permitting us to conduct this webinar. I would like to thank our today's speaker, Dr. Narayanan, for sharing the valuable insights about the evolution of bio-implant materials. Thank you, sir. I would like to thank our HOD for his graceful support extended towards this webinar session. And I would like to thank our fellow faculty members for their wonderful coordination. And finally, I would like to wholeheartedly thank all the participants from different locations for your presence and making this webinar a grand success. Once again, I thank all.
Thank you so much, ma'am.
Thank you. Also,
Thank you so much, sir, for your presence.
for attending this session. Thank you all.
Sir, thank you so much, sir. And for all the participants, thank you so much for your presence.